In this lecture, basically what we want to do is, last time we discussed this modified Goodman diagram and Langer criterion, but because to solve problems related to this, we need to convert this into mathematical form or the equations that we use for modified Goodman and Langer criterion. Obviously, we don't draw these diagrams and draw the sigma A and sigma M points to find out whether the point or the part is safe from fatigue. Okay? We calculate that by using equation. Okay? So we start with the equations for modified Goodman and Langer criteria. So starting with the modified Goodman diagram. So obviously it is a straight line. So you know how to write this equation. Okay? Just let me tell you that we will be using two variables. One is SA and SM, and one is sigma A and sigma M. Okay? SA and SM are the values of alternating and mean stress on this line. Okay? Any value of alternating and mean stress that lies on this line is denoted by SA and SM, while sigma A and sigma M is the generic variable that shows uh, alternating stress and mean stress value at any point on this graph. Okay? But SA and SM are reserved for the alternating and mean stress combination that lie on this line. Okay? So we can say that for this modified Goodman line. Okay? So this is equation is for modified Goodman line. So we can use this y is equal to mx plus c. So I'm not driving this equation. I'm just reminding you that this equation comes from here. Okay? So the slope is negative minus SE divided by SUT, and this variable is SM plus this intercept is SE. Okay? Now rewriting this equation, you can get SE over SE plus SM over SUT is equal to 1. Okay? So this is the equation for modified Goodman line, this line. Okay? And in this form, you can easily see that this alternating stress limit is SE plus SM divided by its limit, that is SUT. Okay? And this equals to 1 would give you all the points on this line. Okay? So this is not a design equation, because for design obviously we want to be below this line. Okay? This is the only equation for this line. And now for design, okay. So what we do for design, obviously we want this sigma A and sigma M to be somewhere below that, and when you multiply that sigma A and sigma M with fatigue safety factor, you get SA and SM. Okay? And fatigue safety factor we discussed last time, that how do we find, we divide this length divided by this length. Okay? So for design, what we do is we replace this SA by fatigue safety factor multiplied by sigma A divided by SE. इसी तरह for SM you have fatigue safety factor into sigma. So for design, obviously we can take NF common and move the other to the other side. So you get this equation . So this is our design equation, okay, that we would use to find the fatigue safety factor. Okay. So for any value of sigma A and sigma M, we can use this to find the fatigue safety factor. If this fatigue safety factor is greater than 1, that means infinite life. Okay. If NF is less than 1, we would have finite life. Okay. And obviously, when we have finite life, we can calculate how much life that is. Okay, and we will see that later how to calculate that. Okay. And so this was for modified Goodman diagram, modified Goodman line, and we also have the Langer line. Okay. So for yield check along Langer line, we write the equation. So similarly, y is equal to mx plus t, and we will have a similar equation to this, okay, but where the limit for SA is also SY and for SM is also SY, okay, is equal to 1. Okay. So this is the equation for this line. Okay. And for design, again we use the safety factor. So NY would be SY over sigma A plus sigma N. Okay. And so this basically is the yield check. Okay. So if NY is obviously greater than 1, that means that you are below the Langer line. That means that there is no first cycle yielding. Okay. And this equation is basically same as comparing the yield strength with maximum. So sigma A plus sigma M basically gives you maximum stress. Okay. So if I look at this graph, okay, so this is sigma M and this is sigma A. So sigma A plus sigma M basically giving you the maximum stress that we are comparing with the yield strength of the material. Okay. And remember, all this discussion is still directly valid for pure loading. Okay. We are only talking about pure bending, pure axial, or pure torsion. Okay. We are not directly looking at combination of those. That we will look at later. So, any question from this? So fairly simple. Okay. So we use these equations for designing against fluctuating stresses in fatigue. So let us now move to a problem related to these quantities when you have both alternating and mean stress value. Okay, so now in this problem, we have cold drawn 1040 steel. Okay. So we have 1040 cold drawn steel, and it's subjected to an axial load that is fluctuating between 0 to 28 kilonewton. Okay? So it is a fluctuating stress, and if you want to be more precise, is basically the case of a repeated load. Okay? So you have this kind of load. Okay? So sigma minimum is basically 0, and maximum would be from 28 kilonewton. Okay? So there is a mean stress which is positive, okay? And you have to remember that this is important. Okay? If mean stress is negative, you do the problem same as we did previously. Okay? You don't need to use modified Goodman diagram. Okay? Basically, augmented modified Goodman diagram is the same as solutions for fully reversible stresses. Okay? But when sigma m is positive, then we need to take care of the problem using the modified Goodman or other failure criterion that we will study later. And we have to estimate the fatigue factor of safety based on achieving infinite life, and also we have to do the yield check. So we can start with, for example, I don't know, let's start with the stress part. So stress obviously F over A, but because there is a stress concentration region, so we would be targeting that. So first we would need the fatigue safety factor. And for that, first look for KT. KT that is directly applicable for this case. So first you would need the D by, this is basically appendix 15(1), I think. So dW would be equal to 6.25 into 0.24. And so that implies KT would be equal to somewhere like 2.44. And similarly, Q for this case, so 1040. So we know where to look for Q is a figure 620. Okay. So 1040 has ultimate strength is equal to 590, and yield strength is about 490 megapascal. Okay. So for these values, and R value is obviously 3 millimeter in this case. So for that, Q is turned out to be about 0.83. So putting it in this equation, you get the value of Kf, that is about 2.2. Now, what is the mean stress? So Kf divided by obviously now F max plus F min divided by 2. Or we can do it individually. First we calculate sigma max, sigma min, and then sigma m, or you can do it directly like this. Divided by 80. So that will give you Kf is 2.2, whereas load is given like this. Maximum load, minimum load is 0, divided by area. And for area, obviously you take this point where the stress concentration, the minimum net area. Okay. So 2 So this is 25 minus 6, you get this length, and thickness is 10. So this would give you the value of mean stress, that is equal to 162.1 megapascal. Now, alternating stress you find by F max minus F min divided by 2, or I can write it 2A, but and that for repeated load, obviously this would be same as 162.1 megapascal. For repeated load, sigma m and sigma a has the same value. Now, okay. Now, so this was the stress part. So now we need to know the strength. Okay. So for this, obviously we start with first SE prime 2.5 SUT because it is less than 1400 megapascal, so we can use this formula. So that would give you 295 megapascal. Then first off, the Barron factors for the actual part endurance limit. So the Ka is there to take care of the surface effects. So surface is cold drawn. Okay, so that means we use 4.51 SUT raised to power minus 0.265. Okay. So our SUT in this case is 590. That gives us about 0.83. KB would be because this is a case for axial loading. For axial loading, the size factor is 1 and load factor is 0.85. And rest, because we don't know any information about this, equal to 1. So that gives us the actual endurance limit as 0.832 into 0.85 into 295. So that would give you the actual endurance limit of 208.6 megapascal. So for this case, we have this SE 208.1 and SUT about 590. So check whether our combination of sigma A and sigma M lies in this region or outside this region. We use the modified Goodman equation for design. Okay? And that is 1 over sigma A over SE plus sigma M over SUT. 1 over 162.1 divided by 288.6 plus 162.1 over 590. So that gives us a fatigue factor of safety of 0.95. So that means according to our modified Goodman criteria, this part will not have infinite life. Okay. So that means that this point lies the sigma A sigma m combination lies outside of this region. Okay. Now what should be our next step? यहाँ तक तो सिंपल था, अब क्या करें?
सर यील्डिंग के लिए चेक करें।
हाँ, फिर उसके बाद if it doesn't yield, then what to do?
सर लैंगर लाइन से कंपेयर करेंगे उसको।
नहीं, लैंगर लाइन से तो कंपेयर कर लेंगे यील्डिंग के लिए, ठीक है, ऑब्वियसली। चलिए पहले हम यील्ड के लिए कर लेते हैं, ठीक है। सो फॉर यील्ड obviously you compare it with the Langer line. So for Langer line, this is the yield check. So SY for our material is 490, and this is, so we can see that this yield safety factor is 1.51. So that means that so that means our combination of sigma A and sigma M, that is 162.1, 162.1, does not lie in this region, okay? Or also obviously not in this region because it doesn't have infinite life, but it also does not yield on the first cycle, okay? So it is safe from yielding, but it is not safe from infinite life, okay? So that means that it is lies somewhere in this region, okay? So now if we look at our problem statement, it states that if infinite life is not predicted, we have to estimate the number of cycles to failure. Okay. Now how do we do that? How do we estimate the number of cycles to failure? And this point obviously maybe more likely to lie here, basically on the 45-degree line, because sigma A and sigma M are equal. So how to find the number of cycles? कैसे find करें? नंबर ऑफ साइकिल्स के लिए हमारे पास कोई इक्वेशन है, हमने पढ़ी हुई?
A and B वाला फार्मूला लगा के
नंबर ऑफ साइकिल के लिए हमने एक इक्वेशन पढ़ी है, SF is equal to A SUT B, और A B के भी हमारे पास फार्मूले हैं। और व्हाट इज द वैल्यू ऑफ SF इन दिस केस? Oh, A N B SUT A N,
सही कंप्लीटली रिवर्सिबल के लिए नहीं है इक्वेशन?
बिल्कुल कंप्लीटली रिवर्सिबल के लिए, तो यही मैं कह रहा हूँ ना, अब हम कैसे यूज करें? Can we get the value of SF from this graph for this case?
सर सिग्मा A और
इसका y इंटरसेप्ट होगा, लेकिन उसकी वैल्यू
हाँ, चलो ये बात समझना सबसे जरूरी है, ठीक है। किसका वाई इंटरसेप्ट होगा, किसका वाई इंटरसेप्ट होगा। आप कह रहे हैं इसकी ये वाई इंटरसेप्ट दिस पॉइंट,
सिग्मा ए का जी दिस है।
नहीं ये पॉइंट, इस पॉइंट की तुम्हारे पास वैल्यू है। दिस पॉइंट इज बेसिकली सिग्मा ए एंड दिस इज सिग्मा एम। ये तो यही है 162.1 है, बट 162.1 could not be fatigue strength because you can see कि वो तो endurance limit से भी कम वैल्यू आ जाएगी आपके पास। endurance limit 208.1 है। इस केस में obviously fatigue strength और जो basically reversible fully reversible stress would obviously be higher than 208.1 because 208.1 is giving you infinite life, ठीक है। So a value higher than 208.1 would give you less than a million cycles, ठीक है। So it would lie somewhere between 208.1 and obviously the ultimate strength that is 590, ठीक है। obviously इसके दरमियान में कोई वैल्यू होनी चाहिए, वो वैल्यू कैसे आए। ये बात आप बिल्कुल सही पहुंचे हैं कि बिकॉज दिस फार्मूला इज फॉर फुली रिवर्सिबल स्ट्रेस, ठीक है। दिस फार्मूला इज फॉर फुली रिवर्सिबल स्ट्रेस, ठीक है। एंड दैट इन आर दिस डायग्राम इज बेसिकली दिस लाइन, ठीक है। सो हमें इस लाइन पे पॉइंट चाहिए, इक्विवेलेंट पॉइंट फॉर दिस स्ट्रेस सिचुएशन ऑन दिस लाइन। We can maybe, if we look at this closely, we can see where we have to go. Sigma A limit was SE, ठीक है। So SF from this diagram would obviously be somewhere between this region, ठीक। This is SF, ठीक है। How to find that fully reversible scenario that is the same for this combination of sigma A and sigma M? सोचें यार, तो मुश्किल बात नहीं। And we basically already talked about this in the last lecture. What does the modified Goodman diagram looks for finite life? वो infinite life के लिए तो हम SE को SUT से ड्रॉ कर लेते हैं। For finite life हम क्या करें? If for example we are given that don't use we don't want infinite life, we want 10⁴ cycle and SF for that is maybe 400 megapascal, ठीक है। So how do we design for combination of sigma A and sigma M? What do we do? Because this region is safe for infinite life. Obviously now we could stress more because we are not going for infinite life but only 10,000 cycles. याद कोई इनपुट दें यार।
सर फिर हम SF और SUT के दरमियान में ग्राफ बनाते हैं।
बिल्कुल, SF और SUT के दरमियान में ग्राफ बनाते थे, बिल्कुल। और नाउ दिस रीजन, एनी कॉम्बिनेशन ऑफ सिग्मा A एंड सिग्मा N इन दिस रीजन इज सेफ। सो अगर इसी को यहाँ पे अप्लाई करें तो क्या हम फाइंड नहीं कर सकते नंबर ऑफ साइकिल्स?
सर फिर हमें 10⁴ को
नहीं 10⁴ नहीं, ये
है।
तो देखे ना इसमें तो ये तो 10⁴ ये तो कुछ भी वैल्यू हो सकती थी, उसके हिसाब से SF की वैल्यू आ जाएगी। यहाँ पे हमें सिग्मा A सिग्मा M का कॉम्बिनेशन पता है, बट हमें पता है कि ये इन्फिनिट लाइफ नहीं है, ठीक है। सेफ्टी फैक्टर टर्न्स आउट टू बी 0.95, ठीक है। सो बेसिकली वी वांट कि व्हेन इज दिस सेफ्टी फैक्टर इक्वल टू 1, व्हाट इज द वैल्यू। देखें इसमें क्या चीज चेंज हो सकती है इस इक्वेशन में, SE एस सिग्मा एम और सिग्मा ए तो अप्लाइड स्ट्रेसेस है, एस यू टी की वैल्यू तो मटेरियल के लिए फिक्स्ड है, ओनली थिंग दैट इज चेंजिंग बेसिकली इज एस ई, ठीक है। बेसिकली वी वांट टू नो व्हाट वुड बी द वैल्यू ऑफ एस ई रिप्लेस्ड बाय एस एफ वेयर दिस सेफ्टी फैक्टर इज इक्वल टू 1, ठीक है। दैट would be the fatigue stress value in which this combination of sigma A and sigma M is providing some finite life, and that finite life we can calculate, okay? So basically what we want is, so if your point is in this region, you want to connect it with SUT, and wherever this cuts on the y-axis would give you the value of fatigue strength, ठीक है। So this is the value of a fully reversible stress, ठीक है। This is obviously some combination of sigma and m. This is fully reversible stress. So what is the value of fully reversible, maximum value of fully reversible stress for failure to fatigue failure to occur, ठीक है। इसमें कोई confusion है? We know that
No,
our
sir.
point lies outside this line, modified Goodman line for infinite life, ठीक है। Now we need to know what is the fatigue strength for which that is fully reversible, ठीक है। So for that we would connect this point to SUT and extend it to meet on the y-axis, ठीक है। And remember, y-axis all points are fully reversible, ठीक है। And what would be the equation for this line? So we just use the same equation. Sigma A, but instead of SE, ठीक है, we use SS, ठीक है। Sigma M SUT equal to 1, ठीक है। So if I write this equation for sigma A, that gives us if I sigma A SF would give you minus sigma M over SUT, and so SF would be sigma A SF would be sigma A divided by 1 minus sigma M over SUT. So this would give you the value of fatigue strength, ठीक है। So basically we are using sigma A and sigma M value to find this value, ठीक है। For this case, ठीक है, where sigma A is 162.1, sigma M is also 162.1, and this is 590, this value comes out to be about 223.5 megapascal. And the value also makes sense. It's near endurance limit because our safety factor was 0.95. Okay, so it doesn't mean, it means we are close to infinite life. Okay, so this fatigue strength turns out to be 223.5 megapascal. Had the endurance limit been this, your fatigue safety factor for infinite life would have been 1. Okay. But now obviously it is less than 1, so you don't have infinite life, we have some finite life. And to use this formula, we also need value of A. So for that, first look at this fraction, that is for 590. So this fraction is somewhere about 0.87. So A would be 0.87 into 590 divided by endurance limit. Okay. that gives you 1263 megapascal, and B is minus 1/3 log of 0.87 into SUT, that is 590 divided by SE, that is minus 0.134. So now we can apply this equation for the case of fully reversible stress. So SF can be the fully reversible stress because value of SF we have found on this Y line, okay, where sigma m is equal to 0. Okay. So for this value, that is 223. Value of A is 1263. So this would give us the number of cycles to failure, that is 586 into 10 to the power 3 cycles. Or we can write it 5.86 into 10 to the power 5 cycles. So that is how we calculate the number of cycles to failure if your fatigue strength, if your fatigue safety factor turns out to be lower than 1. Okay. So so basically we replace in the modified Goodman line equation, instead of SE you would use SF. Okay. To calculate the this point where the line joining sigma A and sigma M and SUT cuts the Y axis. Okay. And then using that fatigue strength, we can calculate the number of cycles. So any questions from this?
सही है, हमें कैसे पता चला है कि हम फाइनाइट लाइफ में गए हैं?
फाइनाइट लाइफ में
एंटर हुए हैं, मतलब हमारा इनफाइनाइट रीजन नहीं है।
ये NF से
सर एक क्वेश्चन था।
हाँ, पहले एक मिनट याद कर
सर एक क्वेश्चन था।
जो एक मिनट, ये जो फटीग सेफ्टी फैक्टर आपने पहले फाइंड किया, ये मॉडिफाइड गुडमैन लाइन इक्वेशन यूज करके, जब व्हेन दैट फटीग सेफ्टी फैक्टर टर्न्ड आउट टू बी लेस देन 1, ठीक है,
Yes, sir.
दैट मींस योर सिग्मा ए एंड सिग्मा एम इज बियॉन्ड दिस लाइन दैट इज जॉइनिंग SE एंड SUT। ठीक है, ये जब
एनी पॉइंट हो सकता है सर, वो
हाँ
एनी पॉइंट हो सकता है जॉइनिंग के ऊपर वाला, ये जो हमने लाइन ज्वाइन की है, इसके
हाँ,
ऊपर
उसके
कोई भी
ऊपर कोई भी
पॉइंट
पॉइंट हो सकता है। ठीक है, फिर हमने यील्ड चेक किया।
Yes, sir.
Then we did the yield check. Yield safety factor was greater than 1. ठीक है, अब अगर yield safety factor भी less than 1 आ जाता है, इसका मतलब है पॉइंट आपके इधर इस रीजन में आ गया, तो फिर तो आपको आगे प्रोसीड करने की जरूरत ही नहीं है, क्योंकि फाइनाइट लाइफ कैलकुलेट करने का कोई मकसद नहीं है व्हेन इट इज डूइंग द फर्स्ट साइकिल यील्डिंग। ठीक है,
ठीक है सर।
अगर if had this been greater than 1 and this been less than 1, that would have meant कि we are in this region। ठीक है, क्योंकि यहाँ पे yielding हो चुकी है, बट ये आपको फटीग सेफ्टी फैक्टर कहेगा कि ग्रेटर देन 1, अगेन फेलियर हो गया। ठीक है, तो उसमें भी हम कुछ नहीं कर सकते। बट नाउ फटीग सेफ्टी फैक्टर इज लेस देन 1 बट यील्ड सेफ्टी फैक्टर इज ग्रेटर देन 1, दैट मींस वी आर इन दिस रीजन। ठीक है, एंड वी हैव सम फाइनाइट लाइफ।
ठीक है सर।
अब ठीक है, ओके, द अदर क्वेश्चन।
सर यही था मेरा, सर जो लास्ट एक्सप्लेन किया हो गया सर क्लियर।
अच्छा ठीक है, और एनी अदर क्वेश्चन?
तो ये जो ऐसा हमारे पास
अगर
है, ये हमारे पास किस साइज की
इंटरफेरेंस आ रही है, दोबारा रिपीट करेंगे?
इस एसएफ के बारे में बताइए, ये जो हमने निकाला है।
जी जी, क्या बताऊं इसके बारे में?
सर ये इन्फिनिट
नहीं, ये इन्फिनिट लाइफ के लिए नहीं है। देखिए, मैं एक मिनट दोबारा से इधर डायग्राम ला के रिपीट कर देता हूँ।
सर, इससे हमारे पास जो फैक्टर ऑफ सेफ्टी है 1 आ जाता है इस वैल्यू पे।
बिल्कुल, इस पे 1 आ जाएगा, इस पे 1 आ
तो
जाएगा।
सर फैक्टर ऑफ सेफ्टी 1 का लाइफ नहीं हुआ?
नहीं, 1 देखें, 1 का मतलब क्या है? ये मॉडिफाइड गुडमैन डायग्राम हर फटीग स्ट्रेंथ वैल्यू के लिए डिफरेंट है, ठीक है। उस फटीग, क्योंकि देखें ना, ये जब मैंने मॉडिफाइड गुडमैन डायग्राम बनाई तो मैंने लिखा यहाँ पे जो SE और SUT को हमने ज्वाइन किया, ठीक है। हमने कहा दिस इज फॉर इनफिनिट लाइफ, ठीक है। एंड अगर आपकी कोई और लाइफ है तो ये लाइन आ जाएगी, ठीक है। सो दीज आर ऑल मॉडिफाइड गुडमैन लाइन, but now this is for infinite life, but all of these, so you can say that n जैसे जैसे n less than 10⁻⁶ cycle हो रहा है, this line is moving upwards, ठीक है, and the value of fatigue strength is increasing, ठीक है। SN कर्व में ऐसे ही है ना, अगर हम इसको SN कर्व से कंपेयर कर लें, ठीक है, so you can see on the SN curve, ठीक है, so this is the value of endurance limit and the fatigue strength values. As the fatigue strength values increases, the number of cycles reduce, number of cycles before failure reduce, ठीक है। so ऐसा ही है इस डायग्राम में भी, ठीक है। SE और इसको ज्वाइन करेंगे तो दैट इज फॉर इनफिनिट लाइफ। वो डायग्राम में जो NF अगर उसको इक्वेशन यूज करेंगे आप, ठीक है, दैट मींस सिग्मा A डिवाइड बाय SE, ठीक है, एंड सिग्मा M डिवाइड बाय SUT। सो ये अगर 1 है तो दैट मींस इनफिनिट लाइफ, ठीक है। बट अगर इस SE की जगह हम कुछ SF यूज करते हैं एंड दैट कम्स आउट टू बी व्हेन so 1, so that means that it does not have infinite life, it would have finite life, and that finite life would be at this number of cycles।
ओके सर।
ठीक हो गया?
एक्सक्यूज मी सर। सर
जी 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 जी।
सर अगर हमारे पास फैक्टर ऑफ सेफ्टी और रीडिंग फैक्टर दोनों 1 से लेस देन हो तो
दोनों 1 से लेस देन हो तो इसका मतलब कि आप पार्ट फेल हो गई है, अब पार्ट आपका इस रीजन, ठीक है।
तो इसका ग्रेटर देन 1 हो तो
दोनों ग्रेटर देन 1 हो तो आप इस सेफ रीजन में,
सर आगे क्या
इनफिनिट
करें?
लाइफ है।
ओके सर।
फिर आगे कुछ भी नहीं करना है यार, फिर आगे क्या करना है तुमने?
सर अगर
और
हमें
क्या
पता
चाहिए?
लग जाए कि फाइनाइट लाइफ है तो
हाँ,
हम सॉल्व नहीं करेंगे उसके बाद?
बिल्कुल सॉल्व करेंगे। अगर हमें जिस तरह इस केस में हमें पता लगा ना कि फाइनाइट लाइफ है तो हमने
और
आगे
सर
सॉल्व किया।
इनफाइनाइट हो गई
फिर हम
फिर
कुछ
सॉल्व
भी
नहीं
नहीं करें,
करेंगे?
फिर हमने यील्ड चेक लाजमी करना है, यील्ड चेक लाजमी करना है, ठीक है। ऑब्वियसली फाइनाइट लाइफ होगी तो फिर आपने आगे क्या कैलकुलेट करना है? यहाँ पे तो इनफाइनाइट लाइफ नहीं थी तो हमें कैलकुलेट करना था कि कितनी फाइनाइट लाइफ है, ठीक है, व्हाट इज द नंबर ऑफ साइकिल। बट अगर इनफिनिट लाइफ आ जाएगी तो फिर उसमें आप आगे क्या कैलकुलेट कर सकते हैं? यील्ड चेक लाजमी करेंगे कि यील्डिंग तो नहीं हो रही है, तो नहीं कि वो फाइनाइट लाइफ इनफिनिट लाइफ तो दे रहा है बट फर्स्ट साइकिल में यील्ड हो जाए,
ठीक है सर, थैंक यू।
ठीक है। एनी अदर क्वेश्चन? ठीक हो गया? Okay, so now this is the failure criterion that you would use most often, and because obviously analytically its use is the most simplest, okay? But that doesn't mean that it is the only fatigue failure criterion. So we have जिस तरह
सर
static,
ब्रेक हो जाए।
नहीं यार ब्रेक ना करें, ब्रेक क्या करनी है, हम जल्दी छोड़ देंगे ना, हम जिस तरह छोड़ते हैं। ये असल में ये चीज़ें अभी सारी चल रही हैं, वाइट बोर्ड वगैरह ये वो, फिर आपको पता ब्रेक करें फिर पता नहीं चलेंगे ना चलें, ठीक है। अभी इंटरनेट चल रहा है, बिजली भी है, कोई पता नहीं बिजली चली जाए, तो जो टाइम है उसको यूज़ करें। तो पहले तो थोड़ा सा छोड़ देंगे, ठीक है। तो ठीक है। So as we had number of static failure theories, we had maximum shear stress theory and we have the maximum distortion energy theory. One was more conservative, one was less conservative. So similarly, and one was analytically easy to use. That is, I'm talking about the shear stress theory, and one is analytically a little bit more difficult to use. ठीक है, not much more difficult, a little bit. ठीक है, that is the distortion energy theory. ठीक, so similarly, we have other fatigue failure criteria. And we saw last time when we justified the use of modified Goodman diagram, we said that if you look at the experimental data for fluctuating stress, it is something like this. Okay? So this is your modified Goodman diagram, and most of the points lie above that diagram. Okay? Most of the points lie above that diagram. So this is basically a very conservative criterion. Okay? Now, if we want a mean criterion, okay, a mean criterion, okay, so that will maybe have 50% reliability, and then we can basically calculate how much reliability our answer has. So that is basically a failure criterion which passes right through the experimental data, and that is called the Gerber criterion. Gerber fatigue failure criterion, or Gerber parabola. So it is not a line, it is a curve which is a parabola. Okay? Modified Goodman was a line, it is a parabola. Okay? It is a better fit for experimental data, but it is obviously less conservative than modified Goodman line. Okay? Then we also have, so if I draw it on the same diagram that we used previously, so this is sigma A and sigma M. So Gerber parabola has same limits SE and SUT, but instead of joining it with a straight line, we join it with a curve. Okay, we join it with a curve, that is a parabola. And so again, any point that would lie inside this would have infinite life. Okay. Any line that lies outside this would have finite life, and you would have to use this Gerber parabola with the yield check. Okay. So Langer line would still be used. Okay. Langer line would still be used. Okay. So when you use Gerber parabola, also use it with Langer line. And if the point, if this sigma A, sigma M combination lies outside this, okay, so then for finite life you do the same जिस तरह हमने modified Goodman diagram के साथ में किया, इसी point को हम इसी parabola के through, similar parabola के through move करेंगे इस point से, तो ये जहाँ पे cut करेगा that will you fatigue strength, and that fatigue strength you can use to find the number of cycles. Another failure criterion, and we see the equations for this. Obviously we use the equation. So first we just go through these failure criterions, and then we can write those equations as well. That is SME elliptic. Okay. So SME elliptic is once again used in some design codes. Okay. शाफ्ट के लिए बेसिकली जो शाफ्ट के डिज़ाइन कोड्स हैं एसमी के, उसके लिए यूज़ होता है एसमी एलिप्टिक डिज़ाइन क्राइटेरिया. ठीक है. एंड व्हाट इज दिस नाउ? ऑब्वियसली elliptic, so as the name suggests, this failure criterion curve, this is a curve, and that is curve instead of parabola, that curve is ellipse. ठीक है. And another difference from the modified Goodman and the Gerber criterion is that instead of joining SUT, ठीक है, instead of joining SUT, this is joins SY. ठीक है. So it joins SY and SUT by an ellipse. ठीक है. So it has a somewhat inbuilt yielding check, okay, but we still use it with combination with Langer line. Okay. Obviously at this end, when sigma m dominates, then obviously it has an inbuilt yielding check. And on this end, okay, it basically approximates the Gerber parabola. Okay, so later we will see these figures superimposed. So you will see that in this region where the sigma A is dominating, okay, alternating stresses are dominating, the results are very similar. Okay, it is in this range where the sigma M is dominating that you have the results are different. Okay. And lastly, another criterion. So if we had to create another criterion, okay, not knowing any experimental data, we can create another failure criterion ourselves also. क्या कोई और एक ये लाइन हो गई मॉडिफाइड गुडमैन डायग्राम की, ठीक है? क्या हम कोई और पॉइंट चूज कर सकते हैं इसको मूव कर दें? कि यहाँ पे हमने अज्यूम किया हुआ है कि सिग्मा m fails at SUT. So we could have also thought about that obviously the failure does not occur at SUT, but failure occurs at SY. Okay? So if we join it with this, so we get this line. So this is basically another failure criterion. Okay? So obviously someone had done that before us. So this is called the Soderbergh failure criterion, fatigue failure criterion. Okay? And this line has an inbuilt yielding check. Okay? So this is the only criterion. When you apply this, you don't need to use it with Langer line, okay? Because all the points lie below the yield line and also lie in the infinite region. Okay? But the problem with this is that it is very conservative. Okay? We have seen the experimental data, because experimental data all lies generally above the modified Goodman line. Okay? So because this line is inside the modified Goodman line, so this is even more conservative, okay, with respect to fatigue. Okay? So it is very seldom used, okay, but for comparison sake, we have also this fatigue failure criteria. Okay? So that are generally found in literature. So any question about this? Okay. So
तो ये सेकंड वाला एक्सप्लेन दोबारा कर दें, लिप्टिक
सेकंड
वाला
वाला कौन सा? अच्छा, सेकंड एस्मी एलिप्टिक जो है, इट कनेक्ट्स द एंड्योरेंस लिमिट विद यील्ड स्ट्रेंथ थ्रू एन इलिप्स. ठीक है, नॉट एसई एंड एसयूटी. Gerber criterion and modified Goodman criterion both use SE and SUT as the limits. ठीक है, one through a line, other through a parabola. ठीक है, whereas the SME elliptic use SE and SY, and same is the Soderbergh. ठीक है, the difference is SME elliptic uses a ellipse, whereas the Soderbergh uses a simple line to connect SE with SY. ठीक है, so Soderbergh में simply line है. ठीक है, एस्मी एलिप्टिक में कर. ठीक है, तो लाइन तो बहुत ही ज़्यादा कंजर्वेटिव हो जाती है. एलिप्स जो है ऑब्वियसली इस रीजन में तो कंजर्वेटिव नहीं है बिल्कुल भी, बट इस रीजन में यू कैन से दैट इट इज अ कंजर्वेटिव क्राइटेरिया. So obviously this is all based on experimental data, and these are curves that are fitting through the experimental data. ठीक है, so these are not something that we are driving from first principles कि okay जी strain energy, जिस तरह हमने distortion energy theory बनाई कि okay if we say that failure occurs through strain energy, then what should be the equation. ठीक है, so this is not something like that. Now the equations that are to be used with these Gerber, SME, elliptic, and starting with. So starting with so yeah, SE and SUT, and Gerber parabola is like this. Okay. So instead of using, obviously now the equation would no longer remain linear. Okay. And once again using SA and SM for points on this parabola, and sigma A and sigma M for points inside that. Okay. So equation of this parabola is basically SA divided by SE plus SM over SUT square, okay, equal to 1. Okay. And where does that equation comes from? This comes from AX square plus C. Okay. Obviously, this is the equation for parabola which is symmetric with respect to y-axis. So we can use this to find this equation. Okay. And that equation is for the parabola. And for design, obviously we use some fatigue safety factor. So NF, so we replace this SA with NF into sigma A plus NF into sigma M is equal to 1. Okay. And now this taking NF out would need some mathematical manipulation. Okay. But if you do that, you get this equation. So a little bit more complicated equation than the Goodman line equation that we had. Okay. But we can use this equation to find the fatigue safety factor for Gerber criterion, and if that Gerber fatigue safety factor is greater than 1, so that means your combination of sigma A and sigma M lies in this region, so it is safe. And we also have to use it with the yield check. ठीक है, yield check को आप उसी तरह sigma A divided by sy divided by sigma A plus M like a line, so it is used in combination with this. ठीक, so if this is less than 1, so that means you are in the finite life region, and अगर yielding नहीं हो रही, so then you can basically replace in this equation, replace SE with SF, ठीक है, and find SF, and for that SF you would use you would find the number of cycles. Now for SME elliptic it is from SE to SY point by ellipse, and equation is SA. Again, SA and SM are points on the ellipse. Okay. SA divided by SE square plus SM divided by SY square. Okay. And obviously this comes from the ellipse equation. You are familiar with it. And for design, we obviously replace this with sigma A and this with sigma N. Okay. So that gives you the fatigue safety factor of 1 over sigma A over SE square plus sigma M over SUT square under. Okay. And again use it with the yield check. Okay. And lastly we have the Soderbergh criterion, ठीक है. So similar equation, then modified Goodman line, but instead of SUT you have SY here, and NF would obviously be 1 over sigma A over S E plus sigma M over SU SY. This is used very sparingly. So where the design is very conservative and you don't want to do the yield check. So these are so the rest of the procedure is same, and all the discussion is whatever we had about the Goodman line is applicable here. Just the equations to use for fatigue factor of safety are different, and you have this. We can, for example, so on this diagram we can see all these failure criteria. Modified Goodman was connecting SE with SUT with a straight line. Then you have the Gerber parabola that connects the same point but with a curve, and better fit for experimental data. Then you have the elliptic line that connects SE with SY, and lastly we have this Soderbergh criterion that connects SE with SY with a line. Soderbergh you can see is very conservative. Elliptic in this region as you can say inbuilt sort of yield check here. And in this region it approximates Gerber line. It's very close to Gerber line. So in the region where sigma A is dominating, sigma M is a very low value. And lastly you have this Langer line, yield line is also called the yield line, as a basically used as the yield check. And for the common criteria, that is Gerber and modified Goodman. You have this tables that are given in your book. So table 6.6, 6.7 and 6.8. So here you can see the safety factor that you have to use for fatigue. So this is the line equation and this is the fatigue factor of safety. This is the line equation and this is the fatigue factor of safety. So basically these are the two things that you are concerned with. First, use the fatigue safety factor if it is less than 1 and yield safety factor is greater than 1. Then for finite life replace SE with SF and find SF. And then SF is equal to A and B is used to calculate the fatigue life. So we can, for example, had we ये जो प्रॉब्लम हमने किया, in this problem, where when we found the fatigue safety factor, that this was equal to 1. Now had we used the Gerber criterion, and found this fatigue safety factor based on Gerber, and I'm not going to write that equation again. We have just seen that equation. So this safety factor would have been about 1.15. So as we have seen from the diagram, basically the Gerber criteria is less conservative than modified Goodman diagram. So you always find the Gerber, this number would be higher for Gerber than for modified Goodman diagram. Okay. So had we used Gerber criterion, we could have said that this part will have infinite life. Okay. And according to Goodman criterion, this part does not have infinite life, it has this life. Okay, any questions? Okay. Next, before talking about the combination load, okay. So all our previous discussion is basically valid for pure loading. Okay. First, we only discussed the fully reversible stresses cases, and then we discussed the cases of fluctuating stresses, but with pure loading, that is only bending, axial or torsion. Okay. And in torsion, okay, torsion obviously we haven't discussed particularly in detail. Okay. That is because we don't use pure torsion. First, pure torsion cases are rare. Okay. And because if you talk about shaft and things like that, there is obviously bending involved with torsion. Okay. So bending load is also significant compared to torsion. Okay. So sometimes we use this directly and mostly in cases of springs. Okay. So we would take up this case when we talk about the spring. Okay. But just as a overview, so everything is same. Okay. Only instead of normal stresses, we would be using shear stresses. So for the shear endurance limit, basically we would be using load factor as 0.59. ठीक है. So endurance limit को जो normal endurance limit है उसको 0.59 से divide कर देंगे multiply कर देंगे तो you would get the shear endurance limit. ठीक. And for shear ultimate strength, you multiply the ultimate strength with 0.67. So that gives you the shear ultimate strength. And rest of the modified Goodman diagram or everything is applicable to this case, pure torsion case as well. ठीक है. So strength ये change कर लेंगे, बाकी उसी तरह tau A divided by shear yields, shear endurance limit हो जाएगी. ठीक है. और अगर modified Goodman diagram की बात करें, इसी तरह tau M divided by shear ultimate strength हो जाएगी equal to 1. ठीक है. So that is basically the Goodman diagram for pure torsion cases. ठीक है. And we will discuss that when we talk about the spring case. ठीक. So now moving on to the case, the last remaining thing that we haven't discussed is the combination of loading modes. So everything that we discussed previously was only applicable to the cases of pure axial, pure torsion, and pure bending. Okay. Now, basically, we want to know that, for example, if we want to apply this equation, okay, then okay, just 2 minutes break. Okay, sorry for the delay. So we were discussing the combination of loads. So that means that instead of pure axial, pure torsion or pure bending, we have combination of these. We want to know basically, and we also have fluctuating stress case. So you want to use the modified Goodman diagram, a modified Goodman equation, but now there is no single alternating stress. You have some bending stress which has an alternating component. We have an axial stress which has an alternating component, and we also have shear stress with alternating component. And these stresses, bending stress also has a mean component, axial stress also has a mean component, and shear stress also has a mean component. So to use this equation in the presence of all these loads, we need an equation that can combine these three values into a single equation. Okay. So, do we know of any equation that can combine these stresses and give us a single equation, single number? So, any equation for stresses which can combine this to give you basically the value of sigma A, and combine these three to give you the value of some sigma M. So have we discussed any equation previously which combines these three values to give you a single value?
The principal stress is
Principal stress principal stress भी है, or any other? More related to failure, I would say.
the distortion energy theory.
बिल्कुल, distortion energy theory. ठीक. So we have multiple methods of basically solving this case, combination of loading modes. We can use principal stresses. One method is called the science method, and in that we also use some principal stresses and some combination. Okay. But the method that we use most often and we would study is the distortion energy method. Okay. So we are already familiar with this. Okay. So we need an equation basically to combine these to a single term. Okay. And we use the distortion energy theory, distortion energy equations to combine these three into a single term. Okay. And experiments have proven that this is on the you can say conservative side. Okay. This result by combining these three with using distortion energy equation and then using modified Goodman diagram same as before. Rest of the procedure remains same as before. Okay. We just combine these loading modes with into a single term. Okay. So for so just for remembering, this was the distortion energy or von Mises stress equation. So that converts all these terms into a single equation, and we can write this in stress form also. Okay. For plane stress, obviously these are the cases for plane stress. Okay. So when we are faced with this combination, what we do is we find the alternating von Mises stress, okay, and that would be, okay. So generally you have the axial, just the shaft ke cases, and you have an axial load on top of that. We basically use this equation, but generally on shaft in under bending, you have only sigma x. Okay? So bending stresses and axial stresses usually are in the same direction, so they superimpose onto each other. Okay? So basically you have sigma bending in alternating component and sigma axial alternating component, and you add those to get sigma x. So ये basically sigma x है, ठीक. And also remember to use fatigue safety factors, fatigue stress concentration factors, and remember that these factors would be different for the same loading and same geometry. This factor would be different for bending and for axial, ठीक है. So kf for bending would be bending loads would be different, kf for axial load would be different, ठीक है. So we use fatigue safety factor or fatigue stress concentration factor with this, and also obviously torque component. So again, this fatigue stress concentration factor for torsional load would be different, ठीक. So we would use this equation, and obviously if you have sigma y components in your problem, then you can write that as well with this, ठीक है. So this will give you the value of sigma a prime and sigma m prime would again be stress concentration factor into the bending load, mean bending load, ठीक है, and mean axial load, ठीक, and mean torsional load, ठीक. So that would give you sigma m value, and we use that. So for example, if you are using the rest of the procedure is same as was for pure loading cases. So for example, if we are using the modified Goodman diagram, so we use this sigma a prime divided by SE plus sigma m prime divided by SU t, for finding the fatigue safety factor for infinite, ठीक. अच्छा, एक दो differences और आएंगे. So this is very easy. You just use Goodman criterion in combination with distortion energy theory, ठीक है. So DE Goodman criterion. So we can say this is distortion energy Goodman fatigue failure criterion, ठीक है. एक दो problems आएंगे. First, obviously, what to use in the size factor, ठीक है. So size factor, obviously, you had this equation for the value of D less 51 and between 2 point something, and okay, and KB was equal to 1 for axial, ठीक. These were for bending torsion, ठीक. Now when you have a combined load को तो आप यहाँ पे combine कर लिया आपने sigma A और sigma distortion energy theory लगा के, but when you are finding the endurance limit for our case, the problem would arise what to do, which equation to use, because we have both bending and axial cases, ठीक? Both bending, torsion and axial cases. So we use KB is equal to with from this equation or equal to 1. ठीक? Firstly, we know that usually the bending torsion loads are dominating, axial loads are much less than bending and torsion. ठीक? And secondly, by using this, we would be on the conservative side. ठीक? So our solution to this problem is, for combined load, we would always use this equation. ठीक? Don't use KB is equal to 1. ठीक? The other problem that would come when we would be calculating the strength would be the load factor. Because obviously we know that load factor is equal to 1 for pure bending, 0.59 for pure torsion, and 0.85 for axial. ठीक है. So what to use in this case? ठीक है. What we do is we use this Kc is equal to 1 for combined load. ठीक है. Because first, obviously, we know that this one Mises stress is basically converting all this combination of stresses into a single normal stress. ठीक है. It's a normal stress. ठीक है. So same as bending or axial. ठीक है. But what do we do is we take care of this factor instead of in the strength. We take care of this factor in stress term. Okay? So instead of multiplying the strength by 0.85, thereby reducing the strength, what we do is we increase the axial stress level by the same factor. Okay? So the alternating stress is basically divided by 0.85 to take care of this factor. Okay? This we don't need to consider because the combined loading, the one Mises stress basically has an inbuilt factor for taking care of torsion. ठीक है. We all know, we have previously seen कि जब pure torsion का हमने केस डिस्टॉर्शन एनर्जी के थ्रू करते हैं तो वो full 0.577 ऑफ द यील्ड स्ट्रेंथ आपको दे देता है. ठीक है. So ये 0.577 के जो फैक्टर है that is inbuilt into this equation. ठीक है. So we don't need to use this equation. ठीक है. This term. ठीक है. So axial के जो safety factor है that is used here. And rest of the procedure for designing is the same. ठीक है. We just use these distortion energy theory equations to combine sigma a prime and sigma m prime. ठीक है. So कोई क्वेश्चन है तो कर लें, बाकी ऑब्वियसली नेक्स्ट टाइम फिर हम इसको अप्लाई करते हैं किसी प्रॉब्लम में. और ऑब्वियसली थोड़ा सा एंड में हमने डिस्कस किया तो इसको और दोबारा से इसमें और प्रॉब्लम भी होंगे तो इसको उनको भी डिस्कस कर लेंगे.